Hey guys, today we're going to take a look at Cartesian equations of lines. So, to begin with, we're going to, I've given you here an equation of a line in slope y-intercept form, and we're going to convert this into vector form, okay? Now this is actually fairly simple, and of course, like before, there are multiple answers to finding vector equations. But this is sort of what I would consider the easiest one to find. So our equation is negative 2/3 x plus 4. So just for a minute, we're going to ignore the plus 4, and we're going to look at the fact that it's y equals negative 2/3 x. So if it's negative 2/3 x, and we use our rise over run here, so we'd have a rise of negative 2 and a run of 3, which would put us right here. Okay, which would give us, we know that our line's going to have that direction. Okay, now it's not going to be there, it's going to be up here, right? It's going to be like that, okay? And we go in both directions. But for our purposes, or for this part, we're just going to forget the y-intercept and assume it starts at the origin, because now we can just look at that and we can see that our direction vector is going to be 3, negative 2. Okay, that's going to be our direction vector. And then we just have to add in the fact that it goes through the y-intercept of 4. And what we can do is we can say that the line is equal to, and we'll just say, the point we go through is 0, 4. Plus t times 3, negative 2, and there we go. Okay, and that's where t is now one of the real numbers. And there we go. Okay, simple enough. All right, I'm going to let you do the second one yourself, but the summary here is that we can say we'll use the y-intercept as the point, okay, and if m is equal to, and we'll call it, let's just call it a over b. We'll say a over b, where a is the rise and b is the run. Okay. Oh shoot! What did I do? Nope, we're cool. We're cool. Okay, then our direction vector, which for right now we're going to say, again, often when you're converting, you'll use m as a vector, which I'll write here that that's the direction vector. Okay, is just going to be, well, that was rise over run, so the run is the x, and the rise is the y. Okay, it is worth mentioning that if it is a negative slope, then you're only going to have one of these values be negative. Oh, excuse me. Okay. So anyway, so there you go. I'm going to leave you the second one for you. Now, alternatively, we can go backwards here. So this first one, example 3, is a fairly straightforward one. Because you can see, so it gives us the point here, which is our y-intercept, 0, 1, so it goes through there, and then we have a direction vector of negative 2, negative 3, okay, which is right, it takes us to there, and so we would just have this as our line, okay. And so you can see by looking at that that's going to be y equals 3 over 2x plus 1. But you can think about this the same way we did before. So we had the m vector here, the slope vector in this case, which is the same thing as direction vector, as being negative, whoops, that's not right, as being negative 2, negative 3. And so that led us to the slope being -3 over -2, which is just equal to 3 over 2, of course. Okay? Now, it won't always be this easy because, of course, we were then just able to use this and put it right in there as your y-intercept. You won't necessarily be given the y-intercept as your point. In the second one here, you can see our y-intercept, or our point is not the y-intercept. So in this case, you're just going to start the same. So we're going to say y equals, okay, and here we can write the rule down here. If m vector is equal to a, b, and then m is going to be b over a. Okay. But anyway, and then we use the point it gives us to figure out. So we've got our slope is -2 over 1, but I'm not going to write that, x, and then plus b. We don't know what b is, but we have a point. So just like way back in grade 9, we can just sub in the point. What is it? Negative, oh, right out loud. -2, 3. So 3, -2, -2, plus b. So we get 3 equals 4 plus b. So b equals -1. So y equals -2x minus 1. There we go. Okay. So, anyway, oh yeah, and then the only other thing that we had to do is we can say use point to determine the y-intercepts. There we go. Okay. So I do want you to try the next two on your own, but for now I'm going to jump ahead. Alright, so we're going to talk about the normal equation, and the normal equation is my least favorite version of the equation, if I'm being honest. So anyway, so consider we've got a line L here, and it passes through a specific point P0, okay, which has x and y of x0, y0, okay. It has a direction vector u. So what direction vectors are perpendicular to the vector u? Well, remember, we can use the idea that if we were to just switch the coordinates, okay, then we can, so in other words, so I would have negative uy, ux, or, that's a vector, or uy negative ux. Okay, those two things are both going to be perpendicular. Okay, so these are called the normal. Okay, it's kind of a weird name for it, but when you have these vectors that are perpendicular to the direction, then that's going to be called a normal vector. Okay, so the so the other thing that we can come up with here is the normal equation. So it kind of jumps ahead. So now you can see what's important here is this guy. So, or before I actually do this, so R0 is the direction vector to P0, that point that it's just a point on the line that we determined up here. Okay, so given that, we can actually come up with what's called the normal equation. Normal equation. Okay, which is just the r vector minus r0 dot n is equal to 0. Okay? And because it's dot product, that will be the scalar 0, not the unit or the vector 0. So that's what the normal equation is. Okay? And the normal equation sucks. So, but anyway, so I'm going to leave these two examples for you. I think originally I had these as find the normal equation, but I'm not terribly concerned if you can find the normal equation right now. So we may come back to that later in the unit, but for now, I want you to just try example 7 and 8 on your own, because I want to jump ahead and talk about parallel and perpendicular lines. So if we've got two lines, L1 and L2, and they have the normal N1 and N2, respectively, we know the two lines are parallel. That's an A, it looks like an E. If and only if their normals are what? So if you would just take, so let's say those two things are the lines, well, the normals would go like that and that. And so you can see that the normals are actually also parallel. Okay? So if the normals are parallel, the lines are also parallel. Whoops, I just dropped my pencil. Oh my goodness. All right. So the two lines are perpendicular. If and only if their normals are. And so again, so let's draw what that would look like. Okay, so that's our two lines, and if I draw our normals, we would have one like that, and we'd have one like that, and you can see that the normals are also perpendicular. Okay. Perpendicular. There we go. Okay. So there we go. That's it for that. And now we're going to look at angles between. So we kind of got just a mishmash of stuff today. We're just kind of, basically we're kind of going through like the stuff we need to remember we cover so we can move forwards. But anyway. So the angle between two lines. So the angle between two lines is determined by the angle between the direction vectors. Okay. So the equation we're going to use to find this is just going to be cos theta is equal to, and we're going to take the two direction vectors. So we're going to have u1 and we're going to dot u2 over, and then we just have the magnitude of u1 times the magnitude of u2. And there we go. Okay, and that's it. So that's how you would find it. All right. So anyway, I do want you to try these last two examples as well, and then we will take them up. So until next time, go Sabres!